Hey, this is Brock Lemire's, and in this video I'm going to talk about resistors and power. Okay, so we have learned two equations. These are the big two equations in electrical engineering. V is equal to IR, which is Ohm's Law, and we also have P is equal to IV. So the power of a system, of any electrical system, is defined by its current multiplied by the voltage across it. Okay? And so if we take these two equations, we can actually start looking at the power in a resistor. Okay? So let's start off with this. Let's say we have, let's do our standard, let's put a voltage plus or minus, let's put 9 volts across a resistor. Okay? And for our resistor, let's make it, 300 ohms. Okay. All right. So we look at this system and we say, okay, so I have the way that's connected is this is going to be plus or minus 9 volts because we connected that terminal to that terminal, that terminal to that terminal. And so it's just by connection, it's got 9 volts across it. And if we come in here, we can do some calculations with Ohm's Law. Say if we can, first we can say, okay, I know that the current is flowing in a loop like this. Okay, so the current is going to flow like this, and it has to go all the way around the loop. And so I can come over here and I can calculate what that current is using Ohm's Law across that resistor. So I can say V is equal to IR, and I know that V is equal to 9 volts. I am looking for I, and my R is 300. Okay, so I take that and I say, all right, what do we do with this? Let's go ahead and divide the left-hand side by the right-hand side, the 300. So let me get the old calculator out here. So what I have is, let's go 9 divided by 300. And we end up with I is equal to 0.03, which is also 30 milliamps. Okay, so that's nice. But we remember we also are interested in the rate of energy that is being consumed by this circuit, which is what we call power. And so if you look at these two equations, P is equal to IV and V is equal to IR, you notice immediately that you could just plug one into the other. Okay, so you can basically just plug that right in there. And then what you get is P is equal to I times substituting that in there, times R. Okay, so we can come up with an expression for the power in a resistor by saying P is equal to I squared R. And we have our first equation that relates resistance, current, and power. And it's like, oh, okay. Let's go ahead and see if that works. So let's calculate the power that is in that resistor or being dissipated by that resistor. So let's come in here and we'll go ahead and plug in some values. So let's see. I calculated my I, which was 30 milliamps, okay, and squared. And then I'm going to come in here and put the resistance, which was 300 ohms, and I want to solve for power there. Okay, so let's bring our calculator over, and this will give us some experience kind of looking at how you enter 30 milliamps. So I'm going to take 30 milliamps, and so I do the exponent 3 negative. That's my 30 milliamps, and what I do now is I can just square that, and then times my resistance, which is 300, and I come up with the power being dissipated in that resistor is 0.27, or said another way, 270 milliwatts. Okay, so there it is. There's our power that's being dissipated in that resistor. Okay, that was fun. Another thing, though, that's kind of interesting is that this equation that we learned about used resistance and it used current. But what if you only had resistance and voltage? We went ahead and solved this circuit for all the known quantities, and that was fine. But what if you ever were in a situation where you only needed, or you only had voltage and resistance? So what other things could we do to substitute? Well, what if we solved for I and plugged it into here instead of plugging V into V? So what if I took this V is equal to IR and I said, okay, V is equal to IR, but I'm going to rearrange it so that I get I by itself. Okay, so I'm going to divide by R and divide by R. And so I'll get I is equal to V over R. And the reason I did that was because now I'm going to substitute this guy into this guy this time. All right, so let's see what that looks like. Let's write it all out. I'm going to come down here and we'll say P is equal to, and I'm going to substitute into I, V over R. Okay, so that was this little fella right here that went into this little feller. And then what I'm going to do is say, okay, then I have just V still there. And what I'm left with is P is equal to V squared over R. And it's like, oh, okay, well, that's kind of cool. Life is good. So now what we're going to do here is let's go ahead and calculate this and make sure that it actually comes up with the same value. Okay, so I'm going to come back to old trusty and say, all right, so what is the voltage across that resistor? It's 9 volts. And what is the resistance? It's 300. So I'm going to come over here and I'm going to say 9 volts squared over 300 ohms. And I'll say, okay, now what do we got? Make sure your brackets are curly or they look like ones. Get a little glare on that calculator, so let me do that. So let's take 9 squared divided by 300, and lo and behold, I get 0.27 watts again. So I got equals 0.27 watts, which what we talk, the way we communicate is 270 milliwatts. All right, life is good. Now it's like, well, we did it. We used resistance to calculate that stuff. You know what? Another one. Let's just close the entire loop and just make sure that P. Let's change it to blue. P is equal to IV works. So let's just look at that and say, P is equal to IV. Does that still work? Well, I have P is equal to the current. So I have my 30 milliamps. So let's bring that down here. So 30 milliamps multiplied by my 9 volts. So I got my 9 volters. And what I get there, let's go ahead and clear this out and say what we got. So I got 30 milli times 9. Oh my goodness, it's 0.27 again. 270 milliwatts. So I solved it using current and resistance. I solved it using voltage and resistance, and I solved it using current and voltage. And so, holy moly, this works any which way you want to look at it. Okay, so it turns out this is kind of interesting. So these calculations are common enough that they create these little graphics. This one's called an Ohms Law wheel, and in this one you actually have the power in here too. So you can quickly look at this wheel and say, okay, what is the equations for power? Well, I'm going to have, here's my V squared over R, here's my IV, and here's my I squared R. So those are the three we just looked at. But what's interesting is that you can rearrange these, two equations into a whole bunch of different forms. So you can solve for current is V over R, current is power over voltage, current is square root of power over R, and then you got voltage, that's P over I and the square root. And so like every variation of these two equations is seen in these wheels that you find every once in a while. Okay, so it's just kind of an interesting graphic. Let's talk about power in terms of consumption and sourcing. Okay, so when I come into this circuit, I had drawn plus or minus 9 volts DC, and I had drawn a 300 ohmer, so 300 ohms right there. And we solved that this resistor dissipated 270 milliwatts. But like we talked about last time, this is what we call the load. All right, the load is what uses the current, all right, or uses the power. But this over here is the source. So if we came over here and said, I want to calculate what the source, the power that the source gave to the circuit. Well, power of the source is equal to power of the load. And so if I said there was 270 milliwatts dissipated in this resistor right here, then what happens is that there should have been 270 milliwatts provided to the circuit by the source. And so you say, well, how can I even find out what the power is given by the source? Well, it's quite simple. This current that we just calculated was 30 milliamps, and that current flows around in a loop around the circuit. So that means that current is absolutely coming straight up through the source. So I can simply just say P is equal to IV, okay, and our power is going to be equal to the current which goes to the source, which is 30 milli, and the voltage, which happened to be 9 volts. We've done this calculation before, so now we're at, let's do it one more time just to prove ourselves, 30 milli times 9, and that's, once again, 270 milliwatts. Okay, so now this is an interesting thing because in a circuit you always have a source and you have a load, And the load essentially dictates how much power it wants to take. The source always provides that amount of power. To show that that's true, it's not like you come up here and go, well, the battery or this, let's say I had a 9-volt battery, it's giving 270 milliwatts, so the load can only have that much. It will take whatever it needs or consume whatever it needs. And so let's do an example where I take that same 9-volt battery. So I'm going to take a 9-volter and let's put it over something that's a different resistor value. Okay, the same exact battery. Okay, the same. Okay, and let's put it across something that's like a 1K ohm. Okay, so now what I'm going to do is I'm going to say, all right, let's solve for the current in the loop. So let's go ahead, and we know by connection that we have plus or minus 9 volts right there. And so all we got to do is say Ohm's Law. So let's say V is equal to I, R. My voltage across that resistor is 9 volts. My current through it is what I'm solving for. And then my resistance is now going to be 1K, which is 1,000 ohms. And so what I can do is I can say I is equal to, I can come along and I can say I'm going to divide 9, both sides by 1K. So I get 9 divided by 1 exponent 3. And I get myself 0.009, which is 9 milliamps. Okay. All right. So life is good. So that means this current right here is 9 milliamps. So now the question is, how much power is being dissipated in this resistor? Well, pick whatever one you want. I mean, we have current, we have voltage, and we have the resistance. Let's do it a couple different ways just because we can. So let's take the power being dissipated, and we'll call it like DST or DSP. That's some horrible writing. So let's do power of load. Power of the load, and that's going to be equal to, what's an easy one? Let's do I squared R. Okay, so I squared R. So that's going to be, we got 9 milli squared over 1K. Okay, and so what I can do here is I can come into here and I can go 9 milliamps squared, and then times that times 1K, and I end up with 0.081, which is 81 milliwatts. So that's what's dissipated. Okay, and so then over here I can actually come over here and let's say what's the power of the source. Okay, and it's like, well, the power of the source is going to be equal to, we know I and V, so I got I and V, and so let's just pump it in. We got ourselves a 9 milliamp, and we got ourselves a 9 volter, and what happens there is I say 9 exponent 3 milli, so 9 milli times 9 volts, lo and behold, it is 81 milliwatts. So now check this out. This is what's kind of interesting. This battery, the same battery, when you put a resistor of equal to 300, it sourced 270 milliwatts. But then in this situation, if you put a different resistor, a 1K, it sourced 81 milliwatts. So the same battery is sourcing a different amount of power. That's because the loads dictate the power. They pull whatever they need, and it is the job of the source to try to provide that. Of course, you can exceed how much the source can provide. So that's part of the design consideration. You might have a consideration where you say you can't pull more than 20 milliamps out of this, and then you'd be like, oh, that one ain't going to work. What would be the difference between these two circuits? We haven't talked about this, but what is the big difference between this circuit and this circuit? Well, this circuit is just going to flat out run longer because the battery will last longer. Okay, so then one final convention that is really important when you talk about power. Okay, so the power, it's the polarity of the way that the current flows. So if you have an element, I'm going to draw like a generic element as like a square. Okay, so we'll just treat it as a black box. If you say that the voltage is that way, okay, and this could be, it could be a voltage source, okay, plus or minus. It could be, plus or minus. It could be a resistor, plus or minus. If the current flows this way, okay, that means it is sourcing power. So if it goes negative to plus, it's sourcing power. If the current is going this way, that means it is dissipating power. Okay, so If it flows from plus to minus, it's dissipating. If it's flowing from minus to plus, it is sourcing. And that, now when you go back to these circuits that we just started with, you probably were wondering, like, I always drew the direction of the current this way. How come I always did that? And it's like, because I could have drawn it the other way, but I just happened to know, because somebody taught me once that this is the way it works, that I know that when you have a source and one passive element, like a resistor, it's going to flow from the negative to the positive of the voltage source, because that's what's sourcing the power, and then it's going to flow from the positive to the negative of the passive element, which is going to be, in this case, the resistor, which is dissipating power. Okay, so life is good. This is awesome. One last thing to leave you with, though. We are only talking about kind of imaginary resistors, right? We're drawing a resistor as if it's just, hey, I got a resistor here. Here it is, and I'm just doing math. Well, it turns out in the real world, it matters what kind of resistor that you have. So, for example, this resistor that I'm always throwing on the screen, this one is it's actually called a 1/4 watt resistor. Well, what that means is that this cannot exceed 0.25 watts of power, or it will burn up. Okay, and if you look at this chart, this kind of shows you a range of different different resistors that are very common in breadboarding. Some have a 1/4 watt, some kind of 1/2 watt, 1 watt, 2 watt, and you'll notice that these go up in power as they go up in size. And there's absolutely ones that are smaller than this, because if you go down to like the surface mount parts on a little printed circuit board, they consume even less power. So when you design, you have to take into account what sized resistor you need. And I'm not talking size like value of resistance. I'm talking about like physical size. You basically start with the circuit. Okay, so let's do an example over here. Let's just go back to our two examples. So here we are right here. Okay, so in this situation, I had this guy right here. I had a resistor that was 270 milliwatts. Well, from this image, that is more than a 1/4 watt. Okay, the 1/4 watt is 0.25. That means I could not use a resistor that is this sized. I would burn this up if I put a 9 volter across it, if it was a 300 ohmer. So I would actually have to use a 1/2 watt resistor. I would have to go find a 1/2 watt resistor so that I didn't heat this thing up so much that it burned up. But what about this equation right down here? What about this case where I grabbed a 1K? Well, in this situation, I only consumed 0.81, and what that means is that I could use a 1/4 watt resistor, and in fact, I could have, let's see, 1 divided by 8 is 125, so a 1/4 watt, or 1/8 of a watt, is 125 milliwatts. I could have actually used even a smaller resistor. So when I get down to these values, I actually could have used some of the small stuff. So that's one more design consideration when you actually start building in circuits. Okay, that is it, and that is resistors and power. See ya.